Good afternoon. I think this was the right time to start. So, yeah, my name is Herbert Jaeger. I'm happy to be here in Günne again. I don't know who of you is here for the nth time. It's a pleasure and an honor and everything to give a course here. So I hope you will also like it. This will be a course on dynamical systems and navigation guide. So, and before I start rolling through the slides, I will briefly outline what is the purpose of this goal and for whom is it designed. So, dynamical systems is a very wide field, and everyone working in the sciences who is modeling some system, social, psychological, or natural, whatever, will use some tool to describe time, at least in most cases. And there are so many. And in different disciplines, there are very, let's say, tailored, specific, traditional sets of tools that are used. The neighboring discipline will probably use slightly different tools, and so forth. And in a sense, I would say there are many more perspectives and mathematical models and approaches and tools than one usually perceives in any given area. And sometimes these tools are simpler and more appropriate than the ones that are sort of handed out to you as standard in your community. This course attempts to give an overview over, I would say, very many different formalisms and approaches to just study temporal developments in all kinds of systems and with all kinds of mindsets. Because there will be so many different ones, I cannot give let's say, any in-depth technical introduction to any of them. So this is more, as it says, a navigation guide, that you feel or get an idea of the diversity of methods and also of the diversity of fundamental views on how you can look at temporal development. So that there are really very fundamentally different ways of how you can try to find access to temporal evolution. So it's not only that I will just sort of throw to you like meat to hungry lions, just batch after batch of method after method. I will also try to order them in by perspectives and by, let's say, fundamentally different approaches. So that's the idea. I hope this is accessible to basically everyone. Well, not to everyone, to all of you. And so there will be maybe one or two slides on the way that maybe are a bit too loaded with formulas, but mostly there's not so very much maths. Okay, so all of this said, I will now start. And this was handed to me, and it seems to work. Everything seems to work here, so that is... So first, one disclaimer. When one hears dynamical systems, then there is something like a major dogma, super thrill, whatever, kind of looking at dynamical systems. And I call it here the ABC, attractors, bifurcations, chaos stuff. So that's the most romantic and, in a sense, the most widely popularized way to look at dynamics. And students going to a class on dynamical systems usually expect to hear about this stuff. You will also hear about this stuff, but only about for 1/6 of the time of this course. So and the rest is about other stuff. Okay? So just that the ones who want to learn about just ABC, you're wasting your time. No, you will learn lots. Okay, so I will start with not going into the modeling methods, but into sort of taking a brief look at the things that are modeled, that you want to model possibly. So, namely everything, a dynamical system is anything that evolves in time. That's the definition. So we are dealing with anything that just is, because well, examples. These are all the things that exist, basically. This should be a comprehensive list of everything. And including things like thinking about things that exist. So everything, really everything. And so why is the theory of dynamical systems a theory of everything? Because it is impossible not to be a dynamical system. The word be means existing, and existing means, I would say, in time. And if you exist in time, you're a dynamical system, period. So there's no escape. Which also means that in a sense, there can never be, I think that's hoping in vain, something like a universal theory of dynamical systems. It has been attempted to have something to find the big underlying universal principles of temporal change, but my personal stance is it's not possible. The world is really full of very different things. And if you want to treat them appropriately, you need to use appropriate methods, and they have to sort of address the diversity of things. So don't hope that, well, you can hope, but you don't expect, there will not be a universal theory. So we have to sort of confront ourselves with a very scattered diversity of approaches and methods. This makes it difficult to study dynamical systems theory because any textbook that you get will look only at let's say a window, a small window, and other textbooks will look at other things. Okay. Yeah, so I want to briefly now give you a list of fundamental dimensions which distinguish different methods to describe dynamical systems from each other. So this will be a kind of, I would say, frightening list. So forget about these. This is, if you want to think methodologically, you have to think about how you cleanly approach modeling. I will just go into the middle of it and say, so one basic distinction is symbolic dynamics, where time evolves in discrete symbolic things like texts, written text is ABCs, letters, or robots that perform sequences of actions, or historical events, or the opening mechanisms of enzymes, of reshaping mechanisms of enzymes in cell membranes. Enzymes, are there enzymes in cell membranes? Are there? The enzymes are everywhere, so they must be there. So they go through configuration changes that can be described symbolically. Versus numerical, so things that are measured by numbers. This is a major distinction by way of the implications for the formalisms that you can use. Or deterministic dynamics, that is, the next thing that happens is, at least in principle, somehow determined from what's happening now. As opposed to, well, non-deterministic and stochastic. These are two different things, and I will later explain in this lecture what is the difference between these two concepts. And whenever you see one of these blue catchwords, this means underneath there's a whole tree of mathematical formalisms that sort of are spinning away from these catchwords. Then autonomous dynamics versus non-autonomous dynamical systems. This word autonomous is used in different cultures in very different ways. In maths of dynamical systems, autonomous systems means the ones that evolve out of their own inner lawfulness, so to speak. They are not externally controlled by noise, by input, by whatever. These are autonomous systems. Physicists, natural scientists, usually when they try to describe dynamical systems, they want to isolate their systems first, an electron or a pendulum, put it into a laboratory, make sure there are no external influences, and then measure or describe the dynamics of the system. They want to make systems as autonomous as possible. And the classical laws of nature are formulated for autonomous systems. Whereas in all other sciences, especially in machine learning, psychology, and so forth, one always, not always, but mostly looks at systems that are influenced by input, sensory input. Humans, we are very non-autonomous systems in this technical sense because we change our behavior according to input. And this makes us technically non-autonomous. And in the last eighth of this lecture, so in 2 days, I want to say something about formalisms for modeling non-autonomous dynamics, which is much more involved than this one and much harder to do. Well, we'll see. So we continue these basic descriptive dimensions. Low dimensional versus high dimensional. This seems like a technical thing. What's the difference between 5-dimensional systems and 10? Seems not very dramatic, but between 5 and 200 million dimensional, that's a difference. And between 200 million dimensional and 2 to the power of 500 dimensional, it's again a difference. And I was just talking about 3 types of systems that are standardly treated. So the 2 to the power of something dimensional, computers are that type of system. 2 to the power of a few hundred? No. What did I say for the second type? So a few million dimensional systems. That is what I would say you easily get in typical machine learning tasks. If you do image processing, then you handle systems of that size. And then low dimensional means 3 or 4. 3 is better than 4. 2 is even better than 3. And this is the classical playground of many of the most celebrated and beautiful theorems of dynamic systems. The higher dimension you get, the weirder it gets, and the more we reach the fields where we do not know how to model. Discrete time, continuous time, just discrete time ticks and clocks, and mathematically this means you have to have an update operator. Continuous time, so it's like physical real time possibly is, and these are described by all kinds of continuous formalisms like differential equations and their sisters and brothers. Linear, nonlinear. Basically, all of the things that I have said before come in 2 main flavors, linear methods and nonlinear methods. The linear methods are much easier, more transparent. We basically understand everything about linear approaches to modeling, whereas nonlinear approaches are often much more advanced, strange, and hard to manage. But there is, it's just one of these basic distinctions that I also will try to illuminate a little bit later. Homogeneous, non-homogeneous. This is my private distinction. So all the other stuff was classical, but homogeneous versus non-homogeneous is my way of looking at things. Homogeneous systems are the ones that can be described with, in a sense, a few concepts. So one classical homogeneous system that has very many dimensions is a bottle of water. It is full of atoms, but all the atoms are the same. And in order to describe such a system, although it's super high dimensional, it's still homogeneous because you don't need very many different concepts to describe what's happening there. As opposed to systems like societies, economical systems, or the brain, you need a very rich vocabulary and a very rich topology to just, in the first place, to describe just what's there, and then proceed from that to describe how it evolves. So, mathematics is produced by mathematicians. Mathematicians are people who basically do not like non-homogeneous stuff. They want to unify everything and want to have the simplest and most abstract and most general descriptions, which is why basically most maths that exist are in a sense geared towards describing homogeneous system. That holds for the physical description formalisms, and the mathematical ones. Non-homogeneous ones are left over to, let's say, Airbus engineers who have to design an Airbus, which is a very non-homogeneous system, but it's not considered science, it's considered engineering. And so no one would expect a beautiful theory of an Airbus with all the stuff from the passenger seat belts to the aerodynamics. But in I would say our sciences, the intelligence sciences, one has to face non-homogeneous systems. Okay, and then finally, stationary versus different flavors of non-stationary. These are systems, stationary systems, that as they evolve through time, their laws of change, their law of evolution doesn't change with them. In a sense, non-learning systems. They are much easier to describe than systems where the law of evolution changes with time itself. These would be adaptive learning and other systems. Finally, there are even worse systems, namely the ones where the laws of the laws change. These would be evolutionary systems. And there is very little maths out there that can cope with evolution, describing evolutionary change. Okay, so this is just to in a sense, confront you from the beginning with many dimensions, and you see already it will be impossible in such a course of only 6 hours to fill all of these, let's say, anchors with the tree of knowledge that's behind it. So in a sense, what I'm saying here is this course will necessarily be superficial, but hopefully still useful. So I will skip this and start directly with the simplest possible dynamical systems and introduce basic terminology now, step by step. And it starts with this, a blue ellipse called x of n. And I call this a state, a system in a state. I will use tomorrow a full session to describe what is a state. It's a very rich concept, but I think as a first approximation, we all have a feeling we know what is the state of the system. You could say it's a snapshot in time. The state of a pendulum, at any time it has some state, and so forth. So states. And for this description of basic ingredients, I will use discrete time. So n means n plus 1, n plus 2, so that I will describe something that evolves in time steps. So if I have a system that has a state at time n, then it probably also had states at previous times, so past history and future. And in order to describe what happens between one time step to the next, one approach, the classical approach in modeling, is to think of something like an operator or a transform or a system function, or there are many names for this. So some mechanism that tells us how this state is transformed into that state. This can take weird formats, so we will learn about a number of such formats, how to describe such transformations. Can be anything from simple functions to complex, or basically Turing machines, for instance. And we also may have two further ingredients, namely such systems may produce output. There again, depending on the discipline in which you live, the output is called measurement or output signal. So signal engineers would call it output signal. Physicists would call it just measurements of some system. So this is the system itself, the pendulum, and you see it, you measure it in angles or velocities, whatever. And statisticians would call it just observations. And such systems can also have input. So at different points in time, something from the outside impacts the system. This can be anything from noise, so just unsystematic disturbances, to control input given, let's say, by a steering device that tries to control the flight path of a rocket. I will use always X as a symbol for states, Y for outputs, and U for inputs. That's the classical U, X, Y. These three symbols are classical in signal processing literature. Okay, so these are basic ingredients. I should maybe say one more. Such a sequence of states is called among others, called a trajectory. So if I use the word trajectory, or sometimes I use the word path, then this means just a sequence of states. Okay. So now I will already contrast two very different views on this basic setup without going into any technical details. So there's one view that I call the natural science view. The natural scientists, as I said before, they look at systems as something that they want to fully understand and exhaustively model, put into a formula, basically. They want to have the purest possible description of a system. So they try in their experiments to isolate the system that they measure and model from external perturbations in sometimes very expensive experimental conditions. So they try to find a way to treat their system without input, without perturbations. They are basically interested in the system internal dynamics, like the laws of gravity, for describing a pendulum. And they want to find basically how can we describe states correctly and adequately, and how can we get this update operator. That's the physical, the classical view on that system modeling in the classical natural sciences, especially physics. And there's something like a very classical formalism, namely ordinary differential equations for doing this. And again, the important thing is the system is isolated, at least conceptually, and these laws of motion that are formulated are at least believed to hold in perfection if the system would be isolated in perfection. Okay. Sometimes these people also have to observe and measure the system. So this Y of part is there in the world of physics, because of course if you have a pendulum, you measure it. So this is there. But in the perspective of these natural scientists, these are only helper things, measurements, that the physicists use to infer back something about the nature of the underlying state. This is for them only a vehicle, so the output, the observations are only windows or vehicles to understand better what's happening inside in the systems. Okay, that's the way to look at dynamical systems and develop mathematical models in the classical natural sciences, as opposed to a very different approach that I call the engineering view. So for an engineer, it's important that the system in the end functions. So this is an engineered system. You don't care, I don't care, how the circuits inside really are set up. I really don't care. But I want it to work. That is, if I press this button, then it should send a signal to that thing, and that thing should communicate with that thing, and then you should see something else. So that's the thing that I want. And the engineers are the people who also want this to happen. So engineers are, by their calling, trained and motivated to design systems that function, that have a well-defined, working, reliable input-output behavior. What happens inside, well, it's maybe interesting for the patent office, but it's not interesting for the user, and it's not interesting for getting good publications or whatever. So the outward functionality of systems is important in engineering. And this has led traditionally to descriptions of dynamical systems that have completely excluded the internal states from the descriptions. So the classical, and I will use also 30 minutes tomorrow to describe this in much more detail, the classical view in the engineering formalisms of signal processing control, their dynamical system development looked like this. Input, output, input, output. What is in between is not modeled. Whether there is, what's in between is not modeled. So the formalisms were just describing relationships between input and output. This is a very different way of looking at systems. Interestingly, at some point, the engineers, but only very late, after Second World War, they became aware that it might be just a clever idea to also model what's happening inside the system. So, and then there was like a revolution in engineering, in signal processing, to also admit state-based models. It was a big thing. And so for 100 years, or let's say 70 years before, states were not existing in the formalisms of engineering to describe dynamical systems. So we will inspect this in more detail tomorrow. That's what I said. Yeah, here. It's helpful to know both. So if you're trained as a natural scientist, you will only learn about formalisms typically that are state-based. If you go through a very classical signal processing school, then you will not hear so much of that. You will hear only about formalisms of that type. And if you are just a poor little human researcher who in whatever field wants to do the right thing, it's just good to know these two things exist and you can pick between the two. Okay, so that was the preamble to this course. So just the big picture. And now I want to start to just visit places and go through a number of classical simple models and so-called finite-state models. You will see what this means, starting with very simple ones and building them up in complexity by adding ingredient after ingredient. And these ingredients that I will be adding are, in a sense, not restricted to so-called simple finite-state models. They will pop up in many other much richer modeling areas. Okay, so in a sense, this is a elementary school of going through a zoo, of models of the simplest kind, but the diversity that we will see already is, in a sense, indicative of what you will see in other formalisms. So the first and simplest one are deterministic finite-state automata, or just DFAs. And any student of computer science who is... did you hear about DFAs of endliche Automaten? Not. Yes. So for computer science, this is very... it's one of the most standard things. Mathematically, such a model, a mathematical model, consists of, first of all, there are only finitely many states. Finite state means this system, as it evolves in time, can only switch between different states, but there are not very many such states. So, for instance, a text can switch only, in a sense, between 28 letters. So it would be a 28-state system. Okay, so and then, according to this model, the transitions between the states, so when it hops from one time step to the next to another, from state to state, are induced by inputs. And because it's a deterministic automaton, the inputs induce deterministic state switches. And everything that can be known about such a system can be written down in a little table where you have let's say here in the columns, the different states, let's say PQR, and then in the columns you have, they are indexed by the the input symbols. Here we have just two inputs, A and B. And this table has to be read in the way, if I'm in state P at some time, input A comes in, I jump to state Q, and so forth. And you could also graphically display this in the so-called state transition diagram, where I think it's clear. So if it's in the state Q at some time, input A comes, it remains in that state, and so forth. And then you could get example trajectories like this. So a state sequence driven by or controlled by an input sequence. And that's it. So, interestingly, do you think this is a useful model? Yes, and you must say yes, because you have learned that all computer science students have to spend half a semester at least on these. So if you now tell them it's not useful, so it must be useful. There's one thing that I think is interesting about this. This seems, all these textbook examples look baby-ish. So 3 states, 2 symbols, a little table. Ha, should we be impressed? No. But if you think about it, a computer, your computer's PC, should be deterministic. So it should be. Okay? So the input signals that go into it, what are they? Well, it's the stuff that either what you type, that's not so high bandwidth, but if it has a network cable plugged in, so then it gets a broad stream of communication input. But it's bits. It's 0 1s basically. So it is symbols. So in fact, your computer is a DFA, or should be a DFA. So the deterministic part should be there. But how big is that state set? How many states does your computer have? Yeah, so a brief, I don't have something to write here. Anyone, by any chance, brought a pen? No, well, not the small ones. I need one. Okay, so I will just outline this in words. No, it doesn't. So I think words are good enough. Yeah. So, a computer, has switching elements, transistors that can be basically, say, 0 or 1. So how many of these gates does a computer have? Well, of course, depends on the brand and everything. But let's just say a few million, certainly, but certainly much more. If you take the memory cells, it's a highlighter. It's highlighter. Maybe. I keep on talking, maybe. So if you have a 2 gigabyte. It's okay? Okay, fine. So how many switchable elements, binary switching transistors or memory cells would you think you have on a computer? I really don't know. But if you have, how many gigabytes of RAM do you usually have today? 16 something? So 16 gigabytes, that's 10 to the power of 16? No. A giga is 10 to the power of 9. And 16, so roughly 10 to the power of 10. Right? So, how many states can such a system have? It has 2 to the power of 10 to the power of 10 billions. That's what we said. So, no, sorry, more. Okay, so first calculate this here, and then 2 to the power of this. Okay, so this is basic combinatorial, that's called combinatorial explosion, what we see here. It has very, very many states. This set Q is finite, but is much bigger than ever we will have atoms in the universe. So this means that, in a sense, when things get very large, such simple sketches lose a bit their meaning. Because what would be the challenge if you just want to describe physical systems, abstract away from them to make time discrete and state discrete, that this model would stick. But the models just get very big. What you will think is what happens then for the poor modeler? Yeah.
Designing T, of course.
Designing T, yeah. This table is then also very big. It's not feasible to write it down. It's not feasible to even write down the state set, except saying how big it is, but you couldn't write it down. The whole thing gets out of hand. You can't do it. There is no way. Instead, you must find further abstractions that abstract away from this. This already looks abstract, but when this thing gets big, you need even more abstract views on this. Okay, so I'm just starting on my mission to confuse you. So I hope I will pick up efficiency and speed. So this is what I just said. So the next thing that also computer science students learn is a little bit more, namely, if you allow these machines or automata while they evolve, so part of this is the same as before, but now when the system is in some of these states, it also, well, people say it emits an observable thing. And again, everything is finite, so there is another symbol set or alphabet, let's say an observation alphabet, and this particular example can emit zeros and ones. And while it does its internal cycling, it also spits out a sequence of zeros and ones, as you see here in this demo trajectory. And such machines are called Moore or Mealy machines, depending on whether these zeros and ones are emitted from the states or from the transitions. Yeah, there's one interesting thing that I should mention. In this example, and in all the other simple models that I'm going to describe today in this session, there are, for all of them, we know methods to infer these models from data. You can call this statistics or machine learning or model inference. The idea is that one does not know this, but one would like to have a model of this kind for the system that one investigates. All one has is data, that is sample trajectories. You have observed the system, you have observed something like this, and now what would be, in a sense, the right or the smallest possible model that explains these data? That's called model inference. So data given, out comes a model that can explain the generation of these data. And for all these models or types of models that I'm going to describe now, such learning algorithms are known. So whenever you would later want to use one of these models types, then you should be confident that if you get data first, then you can get good models out of your data. And the machine learners will help you setting up those algorithms of model estimation. Okay, so now a first relaxation of this of the deterministic picture, talking about non-deterministic finite-state automata. And again, the computer science students must have learned this in their theoretical computer science class. It's basically the same as before, except that the transition function, which was a table before, it's a table again, but before there was a single state only in each of these cells, that is, in the deterministic case, If I'm in some state, get some input, there's a unique next state. Here, in the non-deterministic automata, the possible next states are many, so often are many. Sometimes it's only one, but sometimes you have many several options to go. So, which means that a non-deterministic device is one device or a description of a system that allows different options for trajectories and for things that happen. So here, for instance, for the same input sequence, we could get different state sequences depending on whether this hopping, depending on which of these possible next states are selected in the update process. There is one subtle difference between the word non-deterministic and stochastic or probabilistic. Non-deterministic means something like this, but you will not find a single probability on this table. So there is no additional specification by which probability should this system jump from P to Q or R. So in a probabilistic automaton, you would say go from P to Q with probability 0.3 and from P to R with probability 0.7. Here, nothing like this is said. So in a sense, if you think about non-deterministic automata or non-deterministic temporal evolution, you are interested in the categorical distinction of what is possible. So these two sequences are possible, others are impossible, but you're not interested in how probable they are. The math of non-deterministic dynamics is quite different from the math of probabilistic dynamics. And some of the deepest questions in mathematics, and some claim the deepest question, the so-called P equals NP problem, it's a famous unsolved problem in maths, is directly concerned with non-deterministic models. So I have no time to go into this, but they might look useless and strange, but they, at least computer science modeling needs them. Because I will just say it, I can't resist the temptation, although I lose time, because they can be used to ask questions, fundamental questions about what is possible in computation and what is impossible. So are there problems for which no algorithm exists, period, can't be done, versus problems for which solutions do exist? So this is, in a sense, every philosopher would agree that the distinction between the possible and the impossible is an important and interesting distinction. And theoretical computer science is also concerned with questions asking what is possible with computing and what is impossible. And when you start asking these questions, at some point you end up with non-deterministic models of computing. Okay, that's something we had. So now, sort of the sister to NFA's non-deterministic automata is probabilistic automata. So the simplest kind is known under the name of Markov process or Markov chain, and probably you will have heard the word before. And basically it's just a DFA or NFA equipped with probabilities. So again, we have finite state set as before, and in this case there's no input. Instead, the system trajectory may jump from any of these states to one of the next states, guided by probabilities. And the probabilities are described or can be described in a so-called transition table, where rows and columns are indexed by the states. And basically what you read here, if I am at some point in time in Q1, in state Q1 here, then with probability 0.2, I transit to Q1 again, that is, I cycle back to myself. With a probability of 0.5, I end up in Q2, and with a probability of 0.3, I go to Q3. If you look at the row sum, this is 1, because if you're here, you must go someplace. So these things are exclusive, but exhaustive. So it must sum to 1. And such tables with probabilities where the rows sum to 1 are called stochastic matrices or Markov matrices. Yeah, there's much to say about Markov chains. I just wondered, do I have on the next slide? I don't remember. Yes, I have. So I will say a little bit more about Markov chains. They are, this, in a sense, one of the simplest models to describe what is known as a stochastic process, a process where what happens sometimes happens like this and sometimes like that, so there is randomness in the temporal evolution. And in Markov chains, with the formalism of Markov chains, with this transition table, once you have it, you can compute the relative probabilities, also the absolute probabilities, of particular paths or trajectories. So some trajectories are more likely than others, and you can quantify this and calculate these probabilities. And the formula is, I will just mention it here, the formula that at time 0 I am in state qi0, comma, 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 until at time n I am in state qin. So this is just a particular state sequence of length n plus 1 actually, can be computed as a product of, well, basically transition probabilities. These things are the probabilities. If at some time I'm in a certain state, then I jump to the next time, at the next time to the next state with this probability. So this is one of the numbers in this table. And I multiply all these transition probabilities that I find along the trajectory, plus I multiply it with the probability, what is known as the starting probability. At time 0, where am I? With what probability? That also has to be multiplied into it. So this is the basic formula for describing what is known as the probability distribution in a Markov chain. And the important thing is that we can write it as such a product. This is not typically the case in other stochastic processes, that you can, what is known as factorize this probability into a product. The crucial property of a Markov chain, am I saying here things that are obvious? I don't know. So is that you can do this, namely that the probability of what's going to happen next, that is, the probability on in which state will I be next, at next time step, only depends on where you are at this point. It does not depend on where I've been before. So, and this leads, that's called the Markov property of a physical system, or a system is called Markovian if it has this property, that whenever what happens next only depends on the current state and not on the previous history. So I just wonder whether in the next slide I make some more comments on this. Yes, that's the Markov property, that the probability of where I will be next at time n plus 1, given that I had already a certain history, so that at previous times I have been there and there and there and there and there, that's the same as the probability of being at next time step here, given that I just only know where I've been just at the previous time step. So all of the past history, this stuff here, is forgotten. This is also sometimes why these Markov chains are called memoryless processes. And now comes something interesting. This is not on this slide. The physicists believe that the world is a Markov process. So according to, it's one of the fundamental dogmas in physics. It's basically so fundamental that the physicists don't even know it's there. It's so natural for them. We most of the time don't know that we breathe. We do it. And the physicists do not just explicitly know that they use the Markov property, but they do. Why? Why is that so deeply ingrained in physicists. It is connected to the world view of physics and the natural sciences at large. So I'm not only talking to the physicists here. That it makes sense to speak of the state of a system. Once you say state, you already have committed yourself to the Markov property. Because if you say the system at that time is in that state, and this is the same as saying, if I know that state, I know the rest of the future. If I know the system state, it sort of gives me a cross-section through time, a snapshot of what is the system at this point. That's the state of the system. If I could fully know it, I know all the rest of the system. So, and this is, we will put shadows of doubt on this view in the third session. So, you see, you will have to go through many more technical slides before you come to the fun parts where we talk about nature at large. Yeah.
So you mean we know the past of the thing of the system?
No, in the state of a system, according to physics.
Yeah, because you said given the state, we know the future.
Yeah. We do not know the past. Because different paths can lead to the same state.
Yeah,
but
that's what I was...
yeah, in a deterministic system, a given state leads only to one future.
Yeah.
And even quantum mechanics has not given up this dogma, because most of the time a quantum mechanical system is a deterministic evolution of what is known as the wave function. And so that's very interesting, that apparently Markov property is everywhere according to physicists. According to machine learners, it's nowhere, because maybe I will come to that later. The problem is that you can't observe the state of a system. The full state of a system is usually unobservable. You can only make a few measurements, but they can capture only few aspects of the state. So the state is there according to the dogma, but you can't touch it, so to speak. And if you want to have a system model learned from data, which is what machine learners do, the state is not there, so you can't model it. You can only start approaching it from the outside through observations. And then the Markov property is suddenly gone. And then you end up with lots of fun and trouble. Okay. So, yeah, so I add ingredient upon ingredient. So I feel like what's the English word for conditor? Conditor? Not a baker. So a baker of super cakes and confectioner. How are they called? Confectioner. Okay. Okay. So I feel like a confectioner. So with the DFA, I just sort of baked a plain little piece of cake, and now I put on embellishments one after the other until we have a super Hochzeitstorte, so whatever, wedding cake. Okay, so one of the next embellishments that I will put on is to make a Markov chain, a Markov process controllable. So have external input that interacts or interferes with this random process that goes on. And the model that is used to write down a model for a Markov chain that is influenced by external input is in a sense very brutal. Let's say, again, everything discrete here. If we have, let's say, two different inputs, A1, A2, so Markov chain is going away, but we can give at any point in time an input, either the red or the green one, A1 or A2. Then the mathematical model is very wasteful in a sense in resources. For every input, it simply creates another transition table. So the input basically switches between different local Markov models. That's a very strong way for input to act. It basically switches between different models. And so, well, that's all. There's not much more to say about this. And again, I want to emphasize that there are, for all of these models that I'm explaining today, there are machine learning methods to infer them from data. So if you suspect in your respective discipline that it might make sense to model your system as a controlled Markov chain, then ask in the computer science department for a machine learner, and they will tell you how to infer these models from observation data. Okay. Yeah, and here we come to hidden Markov models. This is one of, I would say, the most useful system models for very broad range of applications, as you will maybe see. So again, this looks like a Markov chain. We have blue dots called states, and the Markov process, these are these orange arrows that allow you to do a random walk between these states. Furthermore, just like in the Mealy machines, at each state we may emit some output, again, from a discrete set of possible observations. Here, just 0 and 1, but it could be any finite set. Okay, so what happens? There's an internal random hopping between the states, giving a state trajectory, and this produces a observable output trajectory, 0, 1, 0, 0, 1, whatever. So in a sense, this is the typical basic setup for most empirical system observations, because an empirical system, according to many typical assumptions, is a stochastic system. So if you try to run it twice, it will not run identically in the two runs. So the system that you're observing, whether it's a human, a mouse, a bee, or a bee colony, or the universe, or an atom, it will be a random system. Physicists will tell you it should be a Markov system, because this is how physics is on the reality. But you are only observing not the state. You don't have access to the state. You have only access to observations. And these observations usually are much poorer in information than the original internal system state. So one usually has a bandwidth problem in observing systems. What you get is much less than what is there. So one gets only impoverished sequence information, and you want to have a model of the underlying real, that means Markovian physical state transition system. Such systems these models are called hidden Markov models. The idea is, what is hidden is the Markov model. What is observable is just the output that it produces. So the data set that you will have is only the observation data, the measurement data. Where they come from, you don't know. So again, this looks like a baby system here. Again, I want to make it clear what this means in real practical modeling. These systems can be very large and very complicated. And the prime system for using hidden Markov models is actually the production of speech, of human speech. Where would be what? So the system output that is measured, these zeros and ones here, would be microphone signals, for instance, speech that a person produces. That is what you observe. What produces this is your brain, plus the vocal tract and all of the physical apparatus. But sort of the most interesting part is probably your brain that does the thinking behind your speaking. And the brain is, according to physicists, a Markov chain. So, therefore, you just ask again, knock door at the end of your corridor where the machine learner sits, and ask him to model the brain, because you have speech data. That should be possible for this person, because I told you they can do it. And again, he will. I would like to see his facial expression, but this is not possible. Why? Yeah, bandwidth, yes. The data are too complex, so this observation already is very complex. Plus, the system behind it is so heterogeneous, complex and high-dimensional, that it doesn't help you to say it's a Markov chain. It really doesn't help you, because in order to properly capture it as a state transition system, the set of states would be as gigantic as the set of states that you at least allow your computer to have. And you probably think you are a bit more clever than your computer. So, no. It depends on how, right? So multiplication of large numbers, computer can do better, but all the rest, still us, right? So, this is also an interesting fact about modeling in general. There may be some models of formalisms, like hidden Markov chains, hidden Markov models, that are certainly correct and appropriate, but still useless because, evident. For instance, because the discrete state set that they assume is just completely unreachable, out of the question for real concrete modeling. You will never be able to publish a model of the brain with a complete state set specified. No? It's just not possible, unthinkable even. Yeah. So these simple pictures that I show here, in a sense, first I argue, don't be deceived by this apparent simplicity and baby nature, because they also hold for very complex systems. But then now I say, hopeless. Once the systems get really complex, it doesn't help you to call them hidden Markov model, because you will not be able to simulate them or compute them or write this down. So, confused? No? I mean, I'm a really poor teacher if I don't manage to confuse my audience with, with a material that's inherently understood by nobody. So if okay, next slide. Comments. I think I did this. Comments. Yeah, that's one thing that is, it's a little item that's worth taking home. These hidden Markov models do not have the Markov property anymore. Although internally they have the Markov property, but externally the process in the observable domain, the measurement time series, that actually are time series that have memory. How is that? So this is a very simple demo case here, how suddenly memory comes into the world. We have a Markov chain that's actually deterministic. So these three states are cycled in between in a circular way. If I'm in P, with probability 1, I go to Q, and so forth. So the internal Markov chain is actually deterministic. When I'm in these two states, I emit a 0. If I'm in this state, I emit a 1. So now I look at the probability distribution only in the output alphabet. So I ask myself questions about probabilities on zeros and ones that I see. So the probability that at the next time step I see a 1, given that at the previous time step I saw a 0, how large is that? Well, when can I see a 1? I can see a 1 here. And that's it. So, and when can I see a 0? here or here. So if I know at the previous time step I saw a 0, this just means I'm here or here. That's all I know then. And then the probability to see a 1, well, if I'm here, I don't see a 1. If I'm here, I see a 1, so the probability is 1/2, roughly. That's what it says. However, if I add more information about the past, in this case, if I know previously I was 0, and even before it was also 0, then I know the state is currently in this state, because only then, this is only the only state that's compatible with having seen 2 zeros. Then I really know where I am, and then the probability to see a 1 in the next time step is 1 instead of 0.5. So in this simple demo example, you already see, if I add more information about the past history, I change my knowledge about this future. So that's a violation of the Markov property. So this is not a non-Markovian stochastic process just on the output. And that's weird. So in a sense, it might lead you to the philosophical jump conclusion that memory or having history is just not knowing enough about the state. Over a beer tonight, we could plunge more deeply into these philosophical questions. More wedding cake stuff. So we add now to a hidden Markov model external input that controls the hidden Markov model. So again, we have an internal Markov chain. However, we now switch between the Markov chains in the same way as we did before with the controlled Markov chain. And we have the output that we know from the hidden Markov thing from the previous slide. These models are also widely used in robotics, at least. And I want to advertise them also for the wider agent sciences. Namely, why? So first of all, how do they mechanically work? Yeah, so again, we have as many internal transition functions as we have inputs. So the inputs switch between different Markov transition laws. So we have blues and red transitions, so to speak, depending on whether the input currently is blue or red. The emission is not switched by the input, so the state emission rules are not switchable by the input. So these systems also can be learned from data. What data? Well, input-output data, but without knowledge of the states. They are sometimes called partially observable Markov decision processes, or POMDP. So in machine learning and robotics, when you say POMDP, people know that you're talking about this. Why are these, in a sense, very natural models to model brain processes? I think every other slide I say these are natural models to model brain processes. Right? It can't be true for all of them. Anyway, I believe it at every point, and whenever I say it, I believe it. So why is that? The idea is that the state set, so these models are placed by robot engineers into the brain of the robot. So that's the way of thinking of a robot according to the thinking of a robot engineer. So really, these systems are implemented as algorithms into the AI department in the brains of robots. So they implement POMDPs. Why does that make sense? These states are the world states the robot thinks exist. So that's the set of states is what the robot has available in its brain to think about the world. So the world, according to the robot's brain, may be in this state or that state or that state or whatever state. The actions are, so the red and green decision making is what the robot does. It's the actions of the robot. Go left, go right, do something. And the emissions here is sensor feedback from the world. So if the world is in a certain state, then the robot can see something of it. So it gets partial information feedback by way of sensory feedback. So this is in a sense a model of how the world reacts to the input from the robot. And the whole thing is very stochastic because, well, robotics is a very stochastic domain. So therefore, these kinds of models are very popular in robot modeling. There's a long tradition called reinforcement learning in machine learning, where the bread and butter type of model are POMDPs. Yeah.
So the inputs, they are not stochastic in the sense as the output is given by this.
No, the inputs are. There is no probability distribution specified for the input. The input is what you can just do as you wish. So it's completely unspecified what input is given at a certain time, because it's up to the operator, so to speak. It's just, yeah. And you may have heard about recent successes in machine learning called deep learning, and that there are now learning machines that learn to play Go in 4 hours by playing games against themselves. Maybe you have heard about this or maybe not. And also inside these systems, there is one department in the learning algorithm that uses POMDPs in order to model opponents and actions and reactions of the world, that is, reactions of what happened on the field if you do something. And because that's stochastic, you need a model like this. Okay, so these are, and I think there is something like, it makes sense to have these models. Reality may be different from this because reality is continuous time and you have continuous sensor feedback. Here everything is discrete and finite. Yeah, a second. But making things discrete and finite simply helps building algorithms that really work. If you would accept reality as something continuous, then there are similar models where everything is continuous, but they are much harder to work with. Therefore, just out of convenience or just plain feasibility, it's often a good design decision for a modeler to escape to a discrete system, and we have seen only discrete system where everything is finite, just because they are easier to handle. And sometimes it really just makes also inherent sense to have discrete systems, yeah?
So that's basically a follow-up to what you just said. What about continuous coactions? Because you pointed out robotics as a field of application, but especially in robotics,
in robotics,
most of your actions are continuous.
Yeah, and sensor feedback is also continuous, and time is continuous. Everything's continuous. Yeah.
So is that still feasible as a model? POMDPs
yes, and not directly like this. So you have to have hybrid formalisms where continuous parts are modeled differently by neural networks, for instance. There's not a single way to do it. It's a challenge. It's really there will be a course here by Barbara Hammer, Machine Learning for Fun. No, The Fun of Machine Learning, something like this, where maybe she will say something about this. I'm not sure, but she could. She knows these things. Okay. Yeah. I'm happy, I'm glad that I'm already here because I planned only for the stuff that we have seen so far for this first session. Now I'm 10 minutes early and I can already go into other stuff. And some of this other stuff just looks good, looks much nicer than what we have seen so far. And so in this way, maybe you get a better take-home feeling when you leave this room, because it's more beautiful. If I click again on this, maybe it runs again. Cellular Automata? No. But if I don't know how to make it run again. You saw that it did something.
I think from the last go back.
Yeah. Okay, so let's see. Yeah, so it's beautiful, right? Or I don't know whether it's really beautiful or strange or whatever, but it's certainly interesting. Okay, so who of you has already been in, let's say, some contact with so-called cellular automata? Oh, wow, super. So then I can be fast. I'm now talking about another discrete model of temporal systems called cellular automata, and the new thing about these is that they are spatially distributed. So here, these are all just pictorial examples, nice examples of two-dimensional cellular automata where what happens in a 2D plane. The systems that we had so far, these state transition systems, they didn't have any spatial geometry. So the states were not arranged on a plane or something. There was simply no geometry. These systems now have geometry, and in the simplest case, they have just the geometry of a line, then they would be one-dimensional cellular automata. Or they have the dimension 2, then they look like pictures. Each state in time is one picture, and the video sequence is just a transition between states. And they can come in higher dimensions as well. Okay, and then they're beautiful. And I will spend a few slides on cellular automata. So the first thing I will explain briefly how they are defined. Again, one has a finite state set. Here, for visualization purposes, just red and green, two states. And a transition function in the simplest case for one-dimensional cellular automata, taking three states into one state. Drawing this transition function means these are three states turn into red. Two red, one green turns into green, and so forth. So that is the full specification of one possible two-color transition function with a three neighborhood. And this leads to temporal evolution, where you combine this very simple local rule with something that's spatially extended. So one system state now is an infinite thing. It is an right-left infinite sequence of blues and greens, greens and reds. That's called a configuration. That's at one time. So it's in a sense a world snapshot of a very large world, but the world is very thin. It's just a colored line. Now we can apply this local transition rule at each of these locations here. So we can pick up, let's say, this little location, check in our transition table what should be the next time color at here. Red, green, green. Red, green, green. It's red. Okay, so at the next time step we color this in red. And it's clear that if we do this for all of these cells in parallel, then we simply get the next configuration. The pictures that you saw on the entry slide did the same thing for two-dimensional environments. Okay, so, and if you iterate this, you get a video sequence, basically, of, in this case, line pictures. If you do it in 2D, you get the video sequences that you saw before. Okay, so a number of comments and pictures. The first thing is that this is a model of spatio-temporal dynamics. So it's not only just temporal dynamics where anonymous states are sort of sequenced, but where something happens in space and the space is important to organize what's happening. Space is here either 2D or 3D or 1D. And what happens in time and in space is dictated by a local rule. Historically, interesting, cellular automata have been invented by John von Neumann. It's hard not to think he was the greatest mathematician of the last century. So he invented basically, do you know, do I have time? 4 minutes. What von Neumann did? So I'm always, so there are many superheroes in the heavens of science. But for me, von Neumann is one of the most superhero-ish heroes. Because he started his career by putting order into quantum mechanics. So he wrote a basic textbooks on the linear algebra or functional, today we call it in German Funktionalanalysis. So the linear, basically the advanced linear algebra of quantum mechanics. So he couldn't bear how poorly the physicists handled maths, and he just wrote a good textbook on this. And so he put order into physics to start with. And then he made numerous contributions in very many branches of mathematics that I just can't tell you because I don't understand what he did. So in basic, I would say every other part of mathematics has been fertilized by him. I know what he did in computer science. So in computer science, he did two things. He co-developed what we today know the von Neumann architecture, which is what your computers do. So CPU, memory, and clock, basically. So that is due to him. Also due to him is Cellular Automata as the basic model of parallel computing, but and I think that makes him a big spirit, catapults him away from just pure mathematicians. He tried to understand what is life. So that is not a simple question. And he wanted to find out what is the basic logical mechanism or ingredients needed for a system to self-reproduce in a spatio-temporal environment. A simple question. So for a mathematician like von Neumann. So he invented cellular automata as a model of self-replicating systems in the late 1950s. Late or early? I don't know. I don't remember. So he designed a system like the ones that you saw, a two-dimensional cellular automaton, where he configured this local transition rule in a way that certain configurations, certain, let's say, picture elements, just reproduced on the screen. They just created copies out of themselves. And von Neumann tried to understand, not only do this. Today, a computer science student would just run a genetic algorithm and try to find a way to do this. But von Neumann tried to get the insight why this happens. What are the conditions to make this possible? So this is not all what von Neumann did. He also invented, or at least co-invented, game theory, which is one of the most important today approaches to understand economical systems. And it's so all von Neumann. And he didn't grow very old, unfortunately. And he was known for the parties that he threw. So there's also very unlikely behavior for a mathematician. So he must have been a very remarkable person. And it's in a sense, so I'm also a very ambitious researcher. And sometimes I feel I want to be an even better researcher. I get even more ambitious, and then suddenly I think of people like von Neumann, and then I see, ooh. So I'm just one of you. So, this puts things sometimes into perspective. So just being aware that however hard you try, you will not reach anything like von Neumann. It helps. It really helps. So that's one other reason why I think von Neumann is such a helpful person to know. Okay, so I will just exactly continue at this point tomorrow morning, I think. I have to check the calendar. So thank you for being with me so far, and hope to see as many as possible of you again tomorrow morning then.